Hi everyone and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's class we will move over from unsupervised learning to back to supervised learning, and we are going to now start studying more and more complex machine learning models. So, in terms of supervised learning, all we have done so far is linear regression, right, and then we looked at variants of linear regression like ridge regression and lasso, right, and we also used that to illustrate concepts like hyperparameter tuning and cross validation, although those are really very important only in more complex models. So, in continuation of our journey, today we are going to start studying the concept of decision trees, and decision trees are a very important class of supervised learning algorithm which is useful for the core engineering disciplines because we often deal with tabular data, right. We have a lot of tabular data wherein you are trying to change let us say the process conditions like temperature, pressure, feed composition in case of a reactor, or you have tabular data of some other form, right, in terms of the rotation rate or some other geometric parameters, and you are trying to relate that to the outcome of your manufacturing process or the materials processing process or kind of the construction strength that you are coming up with. So, whenever you have tabular data, a class of algorithms known as gradient boosted decision trees are very useful, right. So, they are centered on the use of decision trees. So, that is why we are learning the decision tree concept. So, let us go ahead and get started with this. So, today's topic is going to introduce us to decision trees in supervised machine learning. And decision trees are actually very intuitive, right, because they are simply based on binary decisions typically at each point, and then you try to think in a very logical structure. So, a decision tree is a supervised ML algorithm involving a flow chart like structure which consists of multiple decision nodes leading branches leading to a final prediction, right. So, the essential idea is that you are traversing through a tree which is essentially a flow chart like structure consisting of multiple decision nodes wherein you decide which way to go in the tree, to the left or to the right branch, and then ultimately you find one prediction, right. So, it is a nice way of partitioning your feature space. Essentially at every point you are partitioning the feature space, and then you reach a point wherein you are certain that that is what the prediction should be in that part of the feature space, right, and that is how this supervised algorithm works. Alright, so let us write this down. So, the key idea here is to partition the feature space into various domains or various parts such that in each final domain right, which you call a leaf node, you only have a few scenarios or data points, right. Okay. And by scenarios I mean specific class labels in a classification problem. Right. So, if you are trying to classify the soil type, then the specific class labels correspond to the soil type, or if you are trying to classify material as a semiconductor or an insulator or a metal, or if you are trying to classify basically a device or a product that you have manufactured as suitable or not suitable. So, those could be the specific class labels in a classification problem or specific output values, right, numerical values in a regression problem where you are dealing with continuous variables. Okay, so this is the key idea, and I would like to introduce the key idea through the use of an intuitive example hopefully, and this is derived from the domain of materials, right. So, let us say you want to select a material that is for a high temperature component, right. So, material selection for a high temperature component. So, that is what we are trying to do here through the use of an intuitive decision tree, right. So, there are various questions to be asked here, right, and one question for example is how high, right, you want the temperature to be in your process. Is it a high temperature process or a low temperature process? So, let us say that you check, right, whether the operating temperature is greater than a certain threshold, and I am just using this 800 Celsius as an example. So, the operating temperature greater than 800. So, that can be the first question that you ask, and obviously the answer can be only yes or a no, right. So, in decision trees you always only have two branches. So, the answer could be a yes or it could be a no, right. So, that is the first, right, node here, and let me mark it in green here. So, this is a decision node, a node where a decision is made, right, and here, right, depending on your process, right, you may answer yes or no, right, depending on the operating temperature. Alright. So, the next at this point if you say yes, right, then that is where the next question will be asked to further partition the feature space. So, here the feature space is the feature space of the process, right, what operating temperature is there, what kind of material property requirement is there in that process and so on. So, the next question one could ask, for example, is corrosion resistance needed. And again the answer would be a yes or a no. This is again a decision node. So, I am going to mark it in green color. Okay. And if let us say you answered no, that corrosion resistance is not needed, maybe you ask a different question, right, is low weight a critical factor, right, do you need the weight to be low? And based on the answer, right, you may sorry, here actually at no there is a prediction here. You answer no, there is simply a steel alloy here, right. So, this is where you are actually making a prediction. So, I will put in a different color which is blue, right, and here we are asking the next question. So, is corrosion resistance needed? So, if it is yes, right, so we have a nickel based super alloy, that is what we are going to use, and if it is no, then we ask the question, right, is weight a critical factor? okay, and again the answer can be a yes or a no. So for a yes, yeah, we need a light material, so a titanium alloy, and if weight is not a problem, then you go for, let us say, cast iron. Okay. So now you can see that these are the nodes where predictions are made, right, they are marked in blue, and the nodes where you take a decision, right, yes or a no, you answer a question, those have been shown in green here. Okay, so that is how a decision tree works, right. And so you can see that a decision tree can be very versatile. Why? Because you are free to formulate, right, whatever questions you want, and that is what the ML algorithm does, right. When we want to predict something, whether it is a continuous or a discrete variable, when we train the decision tree, right, it is constantly learning what questions to ask so as to reach the final answer. And because of this quality, it is also very interpretable, right, because you were clearly we were able to interpret this tree, right. All we were asking was what kind of operating temperature we are at, whether you need corrosion resistance, whether weight is a factor or not. So the decision tree by themselves are interpretable. However, when we start doing more complex things to decision trees like boosting or bagging or ensembling or other kinds of things, then it becomes less and less interpretable. But to get good performance, unfortunately there is no way to directly use a decision tree. You have to use those strategies, and we will get to those at a later point. Okay, so decision trees are versatile and can be used for both classification and regression. So the kind of algorithm we will study in this course is called classification and regression trees, which are shortened to CARTs or CART, right. So that is the algorithm we will study with respect to a decision tree. So this is the exemplary schematic. We discussed an example, but you can also write down or draw the general structure of a decision tree. So that is what I will do now. So you start at the root node, and then you work through a set of decision nodes, and the decision can be made on the basis of any feature. Let us say you are working with the jth feature, and then if the jth feature is less than c, you come to this branch. If the jth feature is greater than or equal to c, you come to this point, and again you reach a decision node, right. So this is again a decision node, and these decision nodes can finally lead to leaf nodes where a prediction is made. Right, and decision nodes can be followed either by a leaf node or by a decision node. Okay. So this is just a generalized schematic of a particular decision tree, and like we did last time, right, in the previous example I am going to color everything where a decision, right, is required in green, and those parts of the tree where predictions are made in light blue. So these are the leaf nodes, and these are the green ones are the decision nodes, right, and you can link that back to the kind of example we looked at there. Alright, so I hope this kind of a generic structure of a decision tree with a root node, decision node and leaf node that makes sense. Okay, now let us get a little bit more into the mathematics of the decision tree. So how does this decision tree make predictions? That is something that we have to discuss now. So a decision tree partitions the p-dimensional feature space into m regions, and let us say these are R1, R2 all the way up to Rm, and each region then, each region Rk is assigned a constant value Ck, and the regression based prediction of a data point is simply the value of Ck corresponding to the region Rk in which it lies. So as you saw in the example above, right, so each region, right, made a certain prediction. So there is a constant value assigned with a certain region, right, Ck, and then the prediction is simply the value of Ck corresponding to the region in which that data point lies. Okay, so as simple as that. And if you wanted to write it mathematically, right, you can write it like this. So if you denote your decision tree by fx, so it's a, as we have discussed earlier, all machine learning models are function approximators. So you can write it as a function, right, which just makes a prediction. So this function f is representing the decision tree, and that is simply, right, you have to go to each region k equals 1 to n, and you have to check whether the point x lies in that region or not, and if x lies in that region, you simply return the value of Ck, right. So this is how it is written analytically. Of course numerically it is slightly different, but this is a nice way to write it numerically. So to reiterate, m is the number of regions, right, Rk is region k, so k is an index for the regions, and I, as you know, is an indicator function. Okay, and it is a binary function which will return 1 if x is really in Rk, and it will return 0 if x is not belonging to the set of points in the kth region. Okay. So you can see how, right, by writing it this way, you simply make the prediction equal to the constant Ck for the region in which that data point lies, right, because only one term in this whole summation will be non-zero. All other terms will correspond to regions where that point does not lie, and therefore will return 0. Only one term corresponding to the region where this point lies will return a 1. So you will get the constant corresponding to that region, right. So I hope this makes sense. So this is basically how a decision tree works, but now the question is, right, what value do you assign, right, how do you get these Ck's, right. So to obtain the optimal Ck's, we have to minimize a loss function, as is always done in a machine learning model. So to obtain the optimal values of Ck, right, and let us denote these as Ck hat, right, we need to minimize a loss function, and typically, right, we work as always with the sum of squared errors. So, we are going to use the sum of squared errors. SSE. So, let us see what happens when you use SSE as the loss function. So, the SSE is going to depend on the vector of the chosen value Ck for every region, right. So, you have C1, C2 all the way up to Cm, right, those are the variables you have to decide. So, your sum of squared errors will depend on each of those C's, right. So, the SSE is a function of the vector C1, C2 all the way up to Cm, and in shorthand I am just denoting this as C vector. So, this is some I going from 1 to n. So, you have to go over all the data points and check the difference between the true value yi and the predicted value, which is sum k equals 1 to m Ck in times the indicator function of xi belonging to the region Rk. And then of course, this is whole squared because this is the L2 loss that we are using, the sum of squared errors, and here clearly this is the predicted value, and this here is the true value. Okay. So, I hope this makes sense so far, and then like we did in the case of linear regression, to obtain these optimal values of Ck hat, we just have to differentiate the SSE versus the parameter and then set that to 0, right. So, you have to differentiate the loss function with respect to the parameter Ck, and at Ck equals Ck hat, the optimal parameters, this should be 0, right, to find the optimal parameters. Okay, so let us differentiate this sum of squared errors. So, and to make that easy, right, since you have to differentiate with respect to Ck and this k also appears here, this could cause confusion to some of us. So, what I am going to do is I am going to change this k variable here to another variable L, right. So, typically you call these dummy variables, right, because k is inside the summation. So, you could call this k as L, M, N, whatever, and not M here because M is used in another context here, but you could call it O. P is again we have used P, Q, R, whatever you want, but essentially this is a dummy variable, and to ease the differentiation I am going to denote it as L here. So, the SSE, which is a function of the C vector, is sum I going from 1 to n yi minus sum L going from 1 to m, that is the new dummy variable I have introduced, Cl times the indicator function of I belonging to the region RL, and then whole squared. Now, let us differentiate this SSE versus Ck. So, what you will get is you can go take the derivative inside each term, right. So, the summation comes out, and then we have to apply chain rule. So, first you have to differentiate this whole term. So, that becomes twice of yi minus sum L going from 1 to m Cl I, the indicator function of xi belonging to the region RL, times the derivative of whatever is inside the parenthesis here, right, with respect to Ck. Okay. So, that is the application of the chain rule, and as in many machine learning models including neural networks, chain rule is really important, right. So, once you differentiate this, now see that this thing inside the parenthesis, right, the first term here yi, it does not depend on Ck. So, the derivative of that term with respect to Ck will be 0, and if you look at the second term here, there are m terms, right, depending on Cl, but only one of those terms will depend on Ck, right, and that term if you differentiate with respect to Ck you will just get a 1, right, multiplied by the indicator function Rk, right, because it will be for that particular term. So I hope it makes sense what I have written here, okay, and this obviously you have to set it to 0 for getting the optimal value, right, Ck hat. Alright, so let us simplify this further. This 2 obviously will go away, it is just a constant, so it can be pulled out. So this becomes sum I going from 1 to n yi minus sum L going from 1 to m Cl times the indicator function I belonging to the region Rl, and this minus 1, this is also now a constant, right, that is getting multiplied. So we will get rid of it and you just have the indicator function xi belonging to the region Rk equals to 0. Okay. So that is nice, and now we can really simplify this further, leading to the final answer, right. So you can take the term with the minus to the right hand side, right. So the first term becomes sum I going from 1 to n yi times the indicator function xi belonging to Rk, and this is equal to 2 different summations, that sum I going from 1 to n, sum L going from 1 to m Cl indicator function of xi belonging to the region Rl and the indicator function of xi belonging to the region Rk. Okay. And now these are the optimal choices, so I will put a hat on top of it. Now the interesting thing to note here is that this is the product of 2 indicator functions, right, and then L is going from 1 to m, and one of the indicator functions is always for the kth region. So the only term that will remain from this summation will be the term that corresponds to L equal to k, right. So this whole summation becomes just one term, so that is I going from 1 to n times Ck hat the indicator of xi belonging to Rk whole square, right, and this indicator function is what is known as idempotent, right, because it is an operator, right, which when squared becomes itself, right, because the indicator is as seen here either 1 or 0. If you square 1 you still get 1, if you square 0 you still get 0. So I squared, right, indicator squared is simply the indicator itself, and this is called an idempotent operator or a function. So I going from 1 to n Ck hat I the indicator function of xi belonging to Rk. Okay. So that is really nice, and immediately what you see is this Ck hat, right, can be taken out. Okay. So what do you get now? So you get that Ck hat is equal to sum I going from 1 to n yi times the indicator of xi belongs to Rk divided by sum I going from 1 to n of I belonging to Rk. Okay, because this sum Ck does not depend on this I going from 1 to n. So this is the final expression that we get. Okay, I am going to box this up, and this is really nice, right, for reasons that I will reveal to you in a minute. Okay, this is nice because if you carefully see the expression, the numerator here, the numerator is the sum of all the points, right, sum of the feature, right, not the feature, sum of the target variable of the points in region Rk. So, the numerator is simply the sum of the target variable for points in region Rk, and the numerator has an even simpler interpretation. It is simply the number of points in region Rk. That is beautiful, right. What happens if you take the sum of a variable, right, divided by the number of times, right, that variable was measured, that is simply the average value, right. So, in other words, Ck hat is simply the average value of the target variable over all the points that lie in the region Rk, right. So, that is what the decision tree wants you to predict, right. The decision tree wants you to predict for every region simply the average value of the target variable for the points in that region, right. So, this is a very beautiful result in my opinion and forms the basis of a regression based decision tree, right, regression cart, right. So, this is what it is, right. So, now one important question may be coming to your mind, right. So, clearly to compute these, right, you need to know the regions, right. So, to obtain Ck hat, we need to know the Rk's, right, you need to know the region K, and so far we have not given any prescription for determining the Rk's, right. So, that is unknown, right. So, the above expression right needs the knowledge of the regions. So, how are the regions determined? So, the regions are found using an algorithm called recursive binary splitting. Binary because every time you only branch into two regions, and recursive because you keep on doing it again and again and again till you get the desired accuracy for the decision tree, right. So, this algorithm called recursive binary splitting gives the regions for the tree, and the equation above, this equation gives you how the constants for every region can be obtained, right. So, I hope that gives you an idea of some part of the training of a decision tree as to how to decide the average value, right, in every node, right. So, that is what we did by minimizing the sum of squared errors. In the next lecture we will continue our discussion and delve deeper into the recursive binary splitting approach, and we will also discuss how the CART algorithm works for a classification problem. Thank you for joining today, and I look forward to seeing you next time.